Hi everyone, welcome back to this FEADITH Technologies channel with me Dito. So today we are going to see how to model composite at macro scale. So we're going to use a continuum shell elements to model a composite laminate, and let's start. So the model that we are going to create uh, can be drawn like this. We have a rectangle, and then I will have a circular, so there's a hole, and then we're going to pull here. So because of the hole, the expected deformation will be symmetric, and then like this. So this area will be highly stress concentrated, and the failure is expected to happen around this area, right? So let's do it. And this is also important when you're modeling cohesive elements. Not sorry, not cohesive elements. When you're modeling continuum shell elements, you need to do a proper setting for the stacking directions, right? So it's quite similar to uh, cohesive element models. So both of them need proper stacking directions, especially when after you do a lot of partition in ABAQUS. Usually the default stacking direction, it's not good. It's not correctly oriented. So you need to make sure that you checked it and then you correct it. Okay. So let's start by making part uh, 3D, because we're going to use continuum shell. Continuum shell is based on solid geometry, so it's a 3D deformable and solid. Not sure is it solid, or I think it's solid. Yeah. And then let's make it a click here 0.0, and then it's 200 by 25 as usual, and then done. Click no, not yet. Click cancel. No, I still not want to. Oh, let's do it again. Create, and then click here 200 by 20 25, and then you try again to create the center of the hole here. Just put it here wherever you want. So, and then we give a fix here just to make sure the drawing is not moving when we make dimensioning later. So it's just a good practice to make sure that this is the reference point. You will not use it later for the analysis. It's just for the sake of drawing. So when, because for example like this, when you make dimensioning like this, sometimes the one that is moving is not the circular but the rectangle. So the rectangle moves, you don't want to happen. So in this case, I think the distance should be 10, right? No, the distance should be 7.5. Yeah, that's why it's in the middle. And now let's make again from this guy to this guy. It should be 100. So it's right in the center. And then you click X, you click done. And then this is the thickness. It's 2 millimeter. And then click OK. So now we have a plate with hole. This is the one that we are going to do a tensile test on it. We will model it using a continuum shell, and the property is composite materials. But in order to make a good mesh, we're going to make partition here and here and in around the circular. The way we do it is basically by using the datum plane. We need to create datum plane first. Create datum plane offset from principal plane. So I want to make a datum plane here. So this is the YZ cutting plane, right? Because this is Y, this is Z, YZ, and then I offset maybe around 90. Yeah, 90 maybe enough. Yeah, good. And I want to make another one, YZ. The offset now is 110. Okay. So now I have two datum plane. So I can cut this part, the solid geometry with this datum plane. The way we do it from here, uh, just click and then hold, and then this thing will appear. Use datum plane. So partition cell by using datum plane. Click this guy, select datum plane, create partition, then done. And then you need to make partition for this cell. You need to select the cell first and then select the datum plane. For the first one, because we only have one cell, you don't need to select the cell because that's the only cells available there, because it was one cell before, right? Now you make partition. Now it's divided into two cells, these cells, okay? And now you need to choose which cell that you want to partition. So I choose this one and then click done and then select datum plane. This is the datum plane that is going to partition this cell. And now I have this. To make a better meshing, I will make a more partition, but this time I'm going to use this guy. Uh, Click and hold and then move this partition cell, define cutting plane. Okay, you choose the cell, click done, and then use 3 points. So how it works is basically you define the cutting plane by choosing 3 points in that plane. So this is the first, the second, and the third. I will cut it into two parts. Okay, after you got it, you can make it again. I want to cut this cell, click done, 3 point, this, this, and this, repetition, then this one again, 3 point, this, 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 and this, all right, and this again, 3 points, this, and this. The last one is this guy, 3 point, this point, this point, and this point. Okay, click done. Now it's well partitioned. Now we just need to do the next thing is assigning properties, create materials. So you make sure it's elasticity. For a composite materials, you need to do this. Which one? Orthotropic? No. It is engineering constant, I think. Yeah. So this one I'm using the GFPP materials. So if you don't have any value for these, you may want to check this paper. I don't have the paper now. It's still in process, but check my Google Scholars. Uh, you will find a paper and the corresponding material properties there. It's around 34,600. It's around, I forgot the exact number, 4,300. Where is it? 4,300, 0.38, 0.38, and then 0.4, 1,700, 1,700, and then this one 1,450. I'm not really sure, but let's just use it. I mean, it's a dummy material property, but it's really resemble the original properties of the glass fiber polypropylene with 45% volume fraction. Uh, Let me check. Is it recording? Oh yeah, good. Now we want to add Hashin damage. Click here, damage for duct, not ductile, fiber reinforced composite, Hashin. So in ABAQUS, for modeling damage for composite, they have a very limited built-in model. So because they assume that composite is real advanced materials, so people who deal with advanced materials should be able to define their own user-defined materials. So you need to write if you want to model something that has behavior different than Hashin, and then you need to write your own user-defined material subroutine, UMAT or VUMAT if you're using explicit solver. And it's totally different with the LS-DYNA. In LS-DYNA, you have a wide range of material models for composite materials. So if you don't have this restriction on the type of software that you want to use, for example, for your undergraduate project or for any project, your master thesis, you have the freedom to choose software, and this software is available in your lab, the license, and you need advanced material modeling that is not available in Hashin. It's better to check LS-DYNA because maybe they have more options. Not maybe, they have more options, and maybe their options are suitable for your requirements. More than 10 types of material modeling, MET 64, MET 261, 262, many material model for composite. Okay, so we choose Hashin. Usually for this tensile strength, so this is longitudinal tensile strength. This longitudinal tensile strength is basically this one. So let me explain a bit about this. So when you're having a composite materials, let's say this is a ply and then this is the fiber inside it. All right, so when you pull in this direction, so you're pulling in the direction of fibers, what happen is basically usually that your behavior is linear elastic, and then with a sharp, a rapid crack propagation, because it's very brittle materials, right? So once the crack occurs in one fiber, usually you will directly having like a catastrophic failure. So this is the kind of modeling. So what really happening here, that you need to define the maximum stress, sigma max, and then the energy below it, which is called the energy in longitudinal direction. So in this case, the sigma max that suitable for this GFPP. I mean, I'm assuming GFPP now. GFPP means glass fiber polypropylene. The value is somewhere between 700 and longitudinal direction. I don't have. So this is longitudinal compression strength. So when you do compression in composite materials, what happens usually is that the material will have a a crack here because the fiber will have a buckling, so it will be like this. So the material that initially straight becomes like, it's like there's a buckling here. This is called micro buckling, or some people call it fiber kinking. So usually the amount of stresses, imagine if this guy under tension need 700 MPa to make fiber breakage. To make fiber kinking under compression, you usually need a lower stress level, somewhere between I don't know, 0.5 to maybe 0.7 times this guy. So in this case, I'm going to use value around 400 MPa. And then the transverse tensile test, the transverse tensile strength is, let me explain again a little bit. Imagine again, this is a composite, and then this is the fiber direction. Previously, we pull in the fiber direction. Now, the transverse tension is this guy, is this direction. When you're pulling in this direction, the strength that you experience, the strength that is required to break these, because the breakage will happen in the matrix between the fibers. It's not the damage phenomena is not fiber breakage, but matrix crack. So imagine we put cross section here. We take a cross section. What happens is basically you will see the laminate with small fiber like this distributed randomly inside the matrix. So when you try to pull in this direction, what happens is basically there will be crack in the matrix, or sometimes you will have what we call a fiber matrix debonding. So in the interface there will be a debonding. Yeah, so this is the kind of crack that you might see when you do transverse tensile. So because this is the interface dominated or matrix dominated, the tensile strength in the transverse direction usually only requires a low stress to make this breakage. So user in my case, in GFPP case, is somewhere around 20. When you do compression, it's significantly higher, somewhere around 60. And in the shear, also higher, 35. And then it's also 35. Transverse shear strength. All right. Just click OK. And then for this evolution, this is basically the strength. No, the same like the fiber, we need the stress, maximum stress, and then we need the energy. Now we need to fill the energy for the corresponding mode. For the tensile, let's say it's 10. For this one compression, let's say 5, 6. And then for this guy, let's 0.2 maybe, and 0.2, 0.4 maybe, and compression. And now for stabilization, when a damage happens, the damage happen at very rapid pace, and then to be able to simulate that, you need to make some damping to the algorithm, to the numerical algorithm, so that it can converge, it can find the solution. Usually this value is somewhere with 10 to the fourth. So if you're so later when you are in the module step, when you create a step, there's a section called time period. So how much is the process of tensile happening? Usually the default is 1. If you use the default value, then I recommend to use the viscosity coefficient is somewhere between 10 to minus 4. Yeah, this is the kind of damping. So it means that you give the damping way smaller than the time period, so it will not alter your solution from the true solution, but it will help your convergence speed. But of course, you don't want to use the value like 10 to the minus 1, because this is way bigger than this. So you may find solution, but the solution is not the actual solution. You get a wrong solution, right? So you don't want that to happen. That's why you need to use a value that is small enough but helpful enough to make your simulation converge. Okay, so I'm going to use this one. So if you want, you can check with with 3 0 first. Okay, 10 to the minus 4. If it doesn't converge, you can use this 10 to the minus 3. But in this case, I'm using 10 to the minus 3 because I just want to show you guys. I don't want to simulate very long, because now I'm using my laptop. I don't want to burden my laptop to run these heavy simulations. All right, so now it's good. Everything clear. Click OK. And then now we need to make this guy create composite layout. So when you're using composite, this is the place where you need to click create composite layout, and then you use a initial ply count, how many plies that you want to model. We are going to model a quasi isotropic materials, so we are going to use this laminate. How to say, it's a 0, and then there's a 90. Oh, no, it's wrong. There's a 0 there, and then there's a plus 45, minus 45, and then there is a 90, and then symmetric. Okay, so we're going to use continuum shell because this is the solid geometry. If you want to use a plate geometry or 2D geometry, then you need to use conventional cell. But in this case, I'm going to use continuum shell. So in terms of region, I'm going to click all of it. Okay, and in terms of materials, where is it? Why? Oh, oops. Yeah, so it's good. So one direction is in the x directions. So okay, so where is it? Why I cannot see it? Okay, you're not supposed to click one by one. Okay, you can click all of here. Okay, and now you put, because this is 2 millimeters. You let me explain again. The total thickness is 2 millimeters. 2 millimeters. Okay. When I made the solid element, I said the depth equals 2 millimeters. And then this is how many plies? One, two, three, four, and then symmetric. So total 8 plies. So 2 millimeter, 8 plies, it means one ply, the thickness is 0.25 millimeter, right? So the thickness here should be 0.25 for all of them. Then make sure you click this one, make calculated section symmetric. And rotation angle, this is 0, this is 45, this is minus 45, and then this is 90. Okay, and then there's no need to change anything here, and then you click OK. Nice, that's it. And then we go to assembly, we create it easily, and I go to step, we create step static general, and non-linear geometry, you can turn it on if you want. In this case, I don't think you have non-linear geometry here, because the failure is usually at, I don't know, at very low strain, and then there's no like large deflection or large rotation. I don't think I need it. If you think you need it, you can turn it on. 0.01, and then this is minus 10 because you have damage, so you want to make sure that you allow them to do this small time step increment. And then you need to go to general solution control, because usually when you have this damage, you need more iteration to converge. So you want to make sure that you set the ABAQUS, allow them to use more iteration than what it is normally required. Click here and then time increment. This is, if you watch my videos, this is basic step that I did. Usually I use evenly spaced time interval. And here, for because we want to model Hashin, you need to make sure that we click this one here, this guy, and then SDEG if you need, and then Hashin. Okay, and then that's it. And then if you want to make damage, you click here status, I think, and then okay, okay, and then you click here. So same thing for the energy, you put 100, click OK, and then you go again to the interaction. Interaction, you don't need interaction because there's no contact here. Just go to the load. The load is pretty simple. You go to the displacement rotation, you do it like this, and then you make all of them 0, and then here you create another load, and then you do it like this. But in this case, in the x direction, the direction where you pull, you give 5 displacement. 5, oh yeah, 5 is enough. I think 5 is like 2%, or maybe 10, because the length of the samples is 10. So if you give, hey, no, the length of the sample is 200. So if you give 10, it means that you apply global strain of 5%, right? Yeah, okay. Oh, I forgot. Yeah, it's good. Right, you pull it there, and then this is the most important part is this part. Is make sure you click part here. See, it's now all green. Green means that you can use a structured mass here. So I'm going to show you what happens if you don't do proper stacking direction. So I will just leave it like this and click here. I will just put 2, and let's mesh first. See, this is the mesh. What's happening here? I don't know why. Let's make it better. Let's make it 1. Okay. And here, I'm going to use 10. Yeah. Okay. Also 10. Okay. I click here and save here. So I choose. If you want to choose 2 different line, you press Shift and then click. And then all of them 10. Okay. And then if you do it like that, yeah, nice. It's nice, right? It's really good. It's really good. Now you click a sign element type. You want to make sure that you don't model it as a solid, but as a continuum shell here, okay? You create, that's it, no need for viscosity. Element lesson, yes. Maximum degradation, 0.999. You want to make sure that the damage is not equal to 1. 1 means a full failure. It's good. In theory, it should be reached to 1. But in terms of numerical, you don't want to set to maximum equals to 1, because sometime in the algorithms, when you're dealing with this value of 1, your model is something like this. The k prime is 1 minus d is k0. K0 is this initial stiffness, undamaged stiffness. When the damage start, this guy is moving from 0 to 1. And then your current stiffness is basically, imagine if this is 0.5, maybe 0.5 times k0. Now imagine if this d equals 1, what happened is that uh, in some calculation you might need to invert this guy. You divide it by like this, and then when it d equals to 1, you will have infinite. So you want to make sure that you limit the d is equal 0.999 as big as possible, not equal to 1, just to avoid division by 0. Okay, click OK. Yes. So now they are shell elements, and then we set everything correctly. The only thing that we didn't set is the stacking direction. So if you see here, if we click here, see, here is the top face. This is good. If the brown color is on the on this top things, it's good. But if it's here, it means that the stacking sequence is wrong. It's assumed that this, if this happened, it means that they assume that the ply is from this bottom to this guy. So I mean, they have a mistake in the orientation. They shouldn't be like that. But let's see if someone forgot to do it, and let's see what happened in the result of the simulations. So now we set everything correctly. No stack correct. So without any stacking correction, using 4 to speed up, and then I click submit, and then let's see if it's running. I hope there is no problem regarding the model. You know, I found in many places in YouTube videos they try to do simulations, but they don't show the completed simulations. And then when you try, like this one, actually you abort it because maybe you forgot to do something. Let's see. So, pore pressure cohesive should. What is this? I'm missing property definition. I didn't do correctly. What did I do? Uh, this is nice, guy. We're thinking together right now. 8,000 missing element property. I said it right. I think I said it. This guy, assign element type. Oh, let's see again. Assign element type. And I want to make sure that, oh, I choose the wrong one, not cohesive. Continuum shell. Oh my God. Continuum shell. Second order accuracy with enhanced hourglass. Element deletion, yes. Maximum degradation 0.999. Oh my god. And then you click OK. Done. See? So basically you can read from this guy why this guy is talking about a pore pressure. I'm not using pore pressure, so there's something wrong with my element formulation. So now let's submit it. Hope it works now. Let's see, it's running, yeah. So let's click monitor. So let's see if it's run, and then if it's starting to calculate, and then I will pause my videos, and then I will resume again when it's completed. And then after that, it's running, so I will pause, and then I'll resume later. All right, guys, let's come back again. It's been actually an hour since I paused the video, but if you see here, my simulation is not yet finished. Still around 20% of the total. So if we check again, this is the job and results. Yeah, this is, you see the contour only shown here because these are the areas that the stacking directions are properly oriented, while the others are oriented like this. So this is wrong. You understand what I mean? So the one on this side is wrong. So that's why you will never be able to simulate. Even if you can simulate, the result is wrong. That's why you need to make sure that you properly orient your stacking directions in order to achieve a correct simulation. So if we, let's say if we make it maybe 10 times what's in now. So this is strange, right? When you pull it, they're not deforming symmetrically as I said before in my note. I think yeah, I expect something like this, but now it's getting strange. Yeah, it's getting strange like this. That's why we need to fix it. So let's just kill the current simulations and then fix the stacking orientations. We need to go back to the mesh, and then we need to, if you see tools again, let me remind you again. Mesh stack orientation. Only these two parts are correct, while the other part are wrong. So how to solve it? Because this is solid geometry. This is using a solid geometry. You can do it like this using assign stack direction. No, you need to move to part first. And then he will ask you to choose. There's no set, so you need to click all of it. And then you click done. And then he wants you to select a top face. The top faces are colored brown. So you need to do this. This is the top face, right? Yeah. So now this is the top face, this is the bottom face, and all are oriented correctly now, right? So you make sure you do this correction, otherwise your simulation will not be correct, or even if it's finished, even if it's finished, the result is wrong, and most of the time it will never finish because you oriented your samples not appropriate. Okay, so here I check again. It's nice, right? So now let's rerun it again. And then let me start. It's 10:52. If you see my time here is 10:52 now. Click run. When it's running, I will stop again. It's gonna take some time, and but I hope it's gonna be faster this time because we oriented everything correctly. The stacking direction, right? So in this video, in addition to show you how to model the composite, to input the parameters for composite, how to make different fiber orientation in a continuum shell, I also want to emphasize to you that when you're using continuum shell, or if you want to use a cohesive elements, you need to set the proper stacking direction, so that ABAQUS knows which one is the top surface, which one is the bottom surface, and they can do proper calculations. Okay. So now let's see. Now it's running. Then let me stop the video. Let me pause the video, and then I will resume when it's done. Yeah, guys. Let's see again. Let's resume the video. Now it's still running. I don't want to wait because it's a damage simulation. It can take longer. My laptop is not a really good laptop. So uh, I just want to make sure that we did properly. So let's see a result here. If you see a result here, you can directly see this is a correct simulation. You see the stress is good, and you can see the contour from here. This is nice. This is amazing, right? You see? Now you do it correctly. You can see the contour all over the specimen. And then the stress are symmetric. You see that there's this thinning here, and I think the damages start to grow right now. Let's see if we choose this is the fiber matrix. There's no fiber damage yet, but the fiber damage criteria now reaches 1. So if you see the damage start now, there's some area here that damage start 0.7, so it's almost fully damaged. I think there is fiber breakage here. If we wait for quite some time, let's see the monitor. Yeah, if you want, you can wait, but I think it's enough for the purpose of this video today. You can directly see now the fact of this stacking direction is really important to make a correct simulation. So make sure when you work with a continuum shell, you do this stacking correction, okay? And thank you for today. Thank you for viewing these videos. And please don't forget to subscribe to these channels because it means a lot to me. It means a lot. I want to reach 1,000 subscriptions, 1,000 subscriber, and please subscribe, comments, and share this channel below. Thank you very much. Bye bye.